All right, everybody, welcome to IWSS. It's my pleasure today to introduce Galen to talk about Python and how to become a better Python coder is my guess as to what today's talk is about. We all know Galen very well. He's been a great member of the IWSS and always asks great questions. So it's a pleasure to have you on the other side of it today to talk about some stuff you know a lot about. So take it away.
Oh, sorry, Jeff, you need to mention Galen's the first student talk.
Oh, it's the first student talk. I guess I should have known that. You are the first student talk. So yes, thank you for being our first student speaker of the semester.
Fantastic. Okay, I'm going to set a timer here because I have a tendency to freestyle it and lose track of time. So try to stay on time for our schedule today. And thank you so much for having me. So yes, my name is Galen and I'm from the computer science department here at UNBC. And I'd like to talk about, I titled this talk, Practical Approaches to Faster and Leaner Python. What it really is it's a bunch of the things that I either know quite well and some things that I want just people to generally know of that I myself only know of. That is a survey of ways of thinking about making Python faster and leaner in the sense of less memory. So I'll start off with a handful of sort of high-level philosophical points, and then I'll talk about probably the most important thing in almost any language, but I'll show you some Python specific things about profiling, of like checking out how good your program really is. Then I'll discuss some code snippets, some just little pieces of code that we can actually very specifically quantify how long they took, at least on my desktop, which is by far not a high performance machine. And then I'll talk about some miscellaneous topics of caching as a way of improving performance, some language extension stuff, concurrency, and then I'll sort of give an unofficial shout out to Numpy on like there's a lot of people I think that can benefit from using Numpy, and then I'll answer some questions, listen to comments, and if you want to stick around later afterwards, we can have a discussion. So let's jump into it. So the first sort of broad philosophical point is that like performance is not everything. So the sort of metaphor here is sacrificing everything else that matters on the sort of altar of making your runtime and memory footprint better. And that there are other things that matter, like how readable your code is, how maintainable it is. There are your human resources. Like, you know, if I have a choice between spending the next hour trying to crunch out just a tiny bit more performance or just telling it to run correctly, go get a coffee and talk to somebody, I'll usually pick the latter. And there's extensibility, which is, you know, how much you can tweak your code later to have new features or extended features, and the portability to other kinds of systems. All that stuff matters. And of course, the correctness, that your code actually does what you want it to do and it doesn't do what you don't want it to do, right? So all these things are they matter, and they're not synonymous with just performance. So it's a kind of a counterintuitive point that I'm going to talk about how to improve performance, but I'm giving you sort of some philosophical points here to not lose sight of the big picture. All right, this is an old aphorism. I'm not even sure where it comes from, but the best code is the code that is already written, which is to say that, you know, there are packages that do specific things out there where there's just decades of expertise that have gone into them. And so unless there's a particular reason, like you want to practice and learn coding something to understand it better, that's a good use. Or that you really do have something that doesn't really fit into the usual use cases, then absolutely write new code. But you know, don't, for example, Fourier transforms or differential equations or neural networks, there's packages that are just ready to go. They're probably done better than, you know, what you can write up in an hour, right? And the last sort of big picture, this is a staple of computer science, is talking about complexity classes or the sort of asymptotic behavior of a program and how much resources it's going to take up as it runs, as you have a bigger input size to the problem. There's sort of two broad resources we'd like to talk about: time and space. Time is the runtime, of literally how long it takes, and space is the different storage that a machine might have. So of course, the processors themselves, nowadays we have 64 bits, and really it can only handle that much at a time. There's also the cache that sits outside of that, that's like extremely quick, immediate access information. And then most of us have also heard of random access memory. That's a bit stepped removed, but still much faster than having it in hard drive. Going from hard drive to the direct CPU is actually pretty time consuming. So that's a brief discussion of like time versus space. If you look up complexity classes on how hard some of these problems are, they're usually stated in terms of best, average, and worst case of how much it will take up. And a general point about complexity classes is that they have to do with the scalability of how hard the problem gets, sort of, well, literally in the limits as you get arbitrarily large input sizes for your problem. And that you should treat it as a guide for scalability, not as an exact predictive model of what the performance on a machine will be. This plot sort of shows an example of that over some interval, the quadratic time algorithm or data structure or whatever it is actually above the quadratic. Asymptotically in the limit, you'll find that the quadratic is going to be way more expensive than the linear. But over some interval, you can actually find that inferior complexity classes actually have better performance or worse. So profiling, this is the most important thing I'm going to talk about today. Whether you're a Python programmer or not, if you're not profiling, then you're not paying close enough attention to how to make your program better. So what's it about? It's about describing and troubleshooting the performance of your code. And what it especially does is it directs us towards the bottlenecks, the things that are not actually like working particularly well. There's a lot of things in your code that will technically cost a little bit, but they may not be worth your time to fix. You want to go for the things that are really costing you the most. And this also helps remove sort of pointless arguments and discussions and philosophizing about the best way to do something. Just just move on and measure it is the better approach, 9 times out of 10. All right. So at a general high level of your entire operating system, you can start to tinker and prod on how long things take. I'm using a few examples from Ubuntu, but frankly, like there will be similar commands on every operating system. So this one just tells you the time of how long it takes to run some kind of Python script, and it breaks it down into different types of time. If you happen to be somebody who uses this command, you'll already know that the user plus system times here, their sum is what you should care about for your particular process. The real time is actually the time that is used on your process plus whatever other processes the kernel had allocated. So it's not, you don't want to kind of ignore the real time for your particular Python script. And if you want an extremely detailed breakdown of what's happening, you can use, it's got the same name, but it's actually a different program, user bin time, with the verbose command or argument, sorry, that it'll give you some extreme levels of detail of exactly how much CPU usage and like swapping between different resources of cache and memory. So that'll give you a very detailed breakdown. But a more standard cross-platform tool that's associated with Python rather than any operating system is actually cprofile. And what it does is if you call it in the command line like this, of -m just means use a particular module, in this case cprofile, and pass in test.py, that it builds a table and it sticks into a prof file, prof, is that right? I may have the extension letters wrong there, but it puts out a file that basically contains a table of things like how many times functions were called, either primitively or recursively, if you know what that's about, and the total amount of time that each thing took. There's also some per primitive rate versus per recursive rate time available. But also, and very helpful, is that it points you to exactly the file and the line number and the name of that function, so that you can get extremely high resolution information about exactly how much everything took to take in your program. And these files can be very large and overwhelming sometimes. So you can get additional tools like SnakeViz is one that I've used in the past that will visualize graphically the sort of hierarchical function calling that can happen so that it's not quite so overwhelming. Another easy to use tool that's available immediately in Python is Timeit, where you can write little snippets of code and pass it into a string, and it will give you the time that it takes, usually per million, but you can tweak with that as well. And you can pass in global parameters so that if you want something like the factorial function to be available in your little test, you can test exactly how long that takes. But I find that writing and rewriting lots of Timeit testing code is a little bit time consuming. And so you can save yourself time by writing what's called a Timeit wrapper. This is one of my favorites. It's actually written by Martin Hines, who put this on his blog. And this is probably, I promise you, this is the most complicated piece of code we'll look at today. And I won't go through it in too much detail, but the internals of this is basically, we sometimes call it a second order function or a higher order function or a meta function, that it basically is a function that you pass other functions into. And what's built into here is that it will print off some information, specifically what module a given marked piece of code is from and what the name of that function is, and then also how long it actually takes. So this looks complicated, but now looking at how you use it, it's extremely simple. That you use this thing called a decorator, which is just this ampersand with the name of that higher order function, and you just stick it in front of one of the functions that you want to time. And so if you had some test function already existing and it gets used later on, automatically it will print somewhere as the program is running into standard output the module that it's from, the function, and the amount of time that it took. So a little bit of work up front, but this is, in my opinion, a nice way of making use of Timeit. But not everything's about the speed. Sometimes we care about how much memory is being used. And so I want to discuss a little bit of prodding around with the size of the memory footprints of different objects. And for the most part, I have one recommendation that is the best out of these three choices. You'll find it built into Python. There is the magic method of size of with the double underscores. And along with the system standard library that has a get size of command, it will tell you how many bytes the object that is referred to by some references. The problem is that it'll only faithfully tell you the size of the most immediate thing that's referred to. So if you have hierarchical data structures like trees or graphs, that it won't actually tell you the size of the whole tree. It'll tell you the size of the highest level that is referred to for the tree. So if you want something that recursively goes through and checks the proper size of the entire thing, you need to go to third-party libraries. And so pimpler.asizeof is a submodule that does exactly this. And it will recursively go through and tell you in bytes the exact size of some object. And last, this is a thing that I have used exactly once ever. It's pretty technical to make use out of this, but I bring it to your attention because if you're trying to get into a difficult underlying problem of how things are scheduled in terms of loading and how things go onto and off the stack and how return functions and all that stuff work, this is a nice debugging tool. It's simple to just import it. And if you have some piece of written code, in this case, my function of thing, that you can disassemble it, taking it from bytecode back into, well, not into Python code, but into these interpreter instructions. So that is one thing to note, actually, as a difference between Python 3, if there's anybody who still uses Python 2 here, is that Python 3 does convert things to bytecode before passing it into the real-time compiling. And that Python 2, if I remember correctly, does not. But if you're using Python 3, this is a way of kind of getting into some lower level details of what's really happening. Okay, now I want to talk about code snippets. So I'm going to show you like little pieces of code and some empirical runtimes on an actual system. And some of them I'll give an explanation of why they are the way they are, and others I'm just going to have to tell you it's an empirical fact that I'm sure there's a reason, but not all of them are known to me. So the first one is comparing for loops versus list comprehensions, and that it tends to be the case that list comprehensions are faster. And in this example, it is. It's just building a list of the squares of some numbers. But I can tell you a little bit of why this one is faster. It's because with the for loop, inside of that loop, it's l.append. You are actually starting a new call of append every time you loop. Whereas the list comprehension is a kind of context environment where it already knows that the next thing it's going to be doing for however many flops, so to speak, is it's going to be building this list. And knowing that, it doesn't have to like reload the append function. In the back end, it knows that it doesn't have to reload append futilely over and over again. It will have certain subroutines loaded, and it'll just build the list a little bit faster because of that. Multiple variable assignments. This is, to be honest, it's a very small gain and should not be used as an excuse for terrible readability. But it is technically true that if you define some variables in sequence on separate lines, it will run a little slower than if you stick it on the same line. What is actually much better, in my opinion, about this feature is not the performance gain, but actually the fact that of that little syntax at the bottom there of AB assigned to BA. If you had imagined this running sequentially and your goal was to just quickly switch the values, this wouldn't work because you'd have A assigned to whatever B is, and then B assigned to whatever A is. But since we just assigned A to B what B's value is, we have actually just overwritten something instead of swapping them, switching them. So this syntax is actually pretty smart that in the back end, it does what you would intuitively want, which is it just switches the values instead of, otherwise, if you're doing this yourself, you have to create, say, like a third variable, store something temporarily, and then write that in after. Okay, tuples versus lists. So mostly I'm talking about how to their construction, and one syntax that you may be familiar with is you can take a tuple or a list and just multiply them by an integer, and that is shorthand for doing multiple concatenation. So we'll just build a big tuple of ones or a big list of ones, and you can time this, and you can see that they're on different like measure scales here, so to speak, that making tuples in this case was 6.6 nanoseconds versus 0.2 microseconds. And that's a huge difference. Why does that exist? Partly has to do with the fact that if you look into the details of how Python is implemented in the C language, so the interpreter is actually implemented in C, that there's this constant that is set of pytuple underscore max free list. And what that means is that there will be, for tuples that are length of 20 or less, it'll actually cache them. I'm not sure how many it'll cache them. It seems like there's got to be some logic around exceptions to not store too many of them, but suffice to say, caching is keeping it in that really short, quick access area of storage, so that if you have to build new tuples and you're sort of building more and more tuples over and over again, you can reuse them, or the Python will it'll hash a bunch of them together, so to speak. And that ends up being much, much faster. Now, I also mentioned the size of the bytes here. You can see they're really similar. I haven't looked into the implementation details, but it does seem like lists are about 16 bytes, consistently larger than tuples. I think that has something to do with referencing and mutability, but I'm not sure. All right, so string methods. Another class example is to compare the string join method versus the concatenation. Now you can see it's actually string underscore add as a magic function. And that's because of how Python does operator overloading. This special magic function is the one that lets you use the plus symbol for string concatenation. And instead of writing out like a whole bunch of strings and then saying plus, 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 I wrote a lambda function to compare the time to doing just the join function. And what this example shows is that using join, which has, again, in the back end, it has made some assumptions of that in the short run, you're just building a bigger string. So don't reload certain things, that ends up being substantially faster in this case on average. All right, list appending versus NumPy array appending. This one actually surprised me because I had read Oswald's and Gorlick's 2014 book, High Performance Python, where they actually give the opposite advice, and they have really good reasoning, but they claim that the lists will be better at appending and dynamically building large arrays than the NumPy array appending. Ask me later if you want about their reasons for that. It seems like possibly in the last 6-7 years that maybe the implementation of NumPy has changed or something, but I found that actually appending to a NumPy array is substantially faster than appending to a list. Even though in both cases, you have an overhead with the NumPy of building the NumPy array in the first place, and you still have to deal with the fact that you are sort of futilely calling append over and over. Like in both cases, this is not necessarily the best way to build an array of something. It certainly isn't, but just to illustrate the difference between appending in one versus the other. All right, this is a subtle kind of topic of assignments versus copy versus decopy. This is one of those things that you don't see it directly in your code, and so it's easy to kind of forget about it. But Python heavily uses pointers. It has these names that point to things in memory, and when you write code, it's doing one thing or another depending on what you've written. So in this example, we've got a list from 0 through 9, and we have Y is assigned to this list of B and B. And this is actually just assignment. Like Y is pointing to a piece of memory that itself is pointing to B twice in a sort of array order, right? And that means that you're not making full copies of B just because you stuck them inside of another list. This is using referencing in a really smart way. Shallow copy and deep copy are where you are at least partially remaking the object. The gist of the shallow copy is that you're copying some of the structure, but you're still ultimately referencing back to the original. Whereas deep copy, you are making a complete separate copy. Inevitably, the latter takes more time and resources, literally more memory as well, to have full copies of things. So the rough rule of thumb here is, try to stick to using pointers in assignment rather than full copying as the kind of rule of thumb for performance. Generators. Now, out of all the code snippets, I'd say that this is the one that I was most surprised by. And I'm not sure how many years I've known about this one, but it is a huge saver on the memory side of things, especially. That it can be very tempting to write a function or a line of code with some, say, list comprehension, where you build up the entire iterable and then you loop over the iterable. With generators, instead, you are constructing the elements of the iterable as you ask for them. Syntactically, it's very simple. Instead of having a function with a return statement, you instead replace that with some slightly adjusted code, but primarily the distinction to tell if your code is a generator versus a function is whether there's a return statement or a yield statement. Yielding means I'm just going to give you the next piece, whereas returning means like this is the final chunk of data that I'm giving you, and then I'm done, right? So with this little example, I assign test of 100 to G, and you can call the next method, and that will give you literally the next element in this iterator, and you can ask for them one at a time. This has the effect that because you haven't loaded this entire giant iterable into memory, that you are not using that memory futilely, right? You are basically going to take an element, do what you want with it, throw it away, and get another element instead of having the whole thing. Hopefully, I've been a little bit repetitive there, but I want to emphasize that that's the key to what generators do to save memory space. They can actually sometimes also improve the time performance as well, for a less direct reason, that if you're making some kind of giant thing in memory, that you can actually overflow the cache or RAM, and that ends up having to do a bunch of restructuring of how things are organized. And that inevitably takes time. So sometimes generators save you time as well as space. All right, control flow, or if else kind of reasoning, branching, if you like, that I wanted to do a comparison of conditional comprehensions versus the Numpy piecewise function. So instead of having like if, elif, else type of statements, you might want to try to avoid dynamic typing by trying to use Numpy's piecewise function. In this example, we just construct an array of data of some numerical values, and I call it the signum, as in the like sign function, but it's sort of a half sign function because it only does -1 and 1. And there's no 0, but suffice to say, the point is it's a function that will return some numerical value based on an if else kind of branching. And that if you time that with the conditional comprehension statement, you get 18 microseconds versus with Numpy, the piecewise function, you have to do some separate things. You have to pass in the data. You actually have to pass in an iterable of the pre-computed Boolean conditions on which branch to go down. But then you also give a final iterable of what value is returned under those different branch conditions. And so there can be a bit of overhead, especially for small data sets, to check these inequalities and then pass in which branch to go down. But compared to the cost of the dynamic typing, overall, it is usually faster and scalable to use NP piecewise and do the branching in a pre-computed way rather than checking it dynamically in the back end a Python loop. Okay, this is a piece of negative advice. People like to talk about NumPy always being the super fast performance improvement, and in many ways that's very true because it gives you statically typed loops on the back end. But on the front end, it's dynamic. Or I should say that with NumPy vectorized, people have this impression that this will suddenly make their functions super, super fast. And that turns out to not be the case because, well, let's get into this example on the top that we have np.vectorize of a bool function. And what this does is it gives you the kind of array broadcasting, right? Normally bool can only be passed. If you pass bool as a vanilla Python function on, say, an iterable, it'll tell you basically whether that iterable is empty. But if you actually want to check if the elements of that iterable are empty, then you can, as a bit of syntactic sugar, apply np.vectorize to this function and then call that on an iterable. And so it'll return an array where you get all the true falses for whether those elements were empty. And that turns out to be actually slower than the list comprehension. That if you just done I for I in map, passing in the bool and data, that actually runs faster. And the reason is that with that while np.vectorize will give you a loop on the back end and give you the array broadcasting type syntax, that it's still a dynamically typed loop. You're still checking again and again in a futile way. Is it still an int or a bool or whatever? And that just takes more time for that dynamic typing. So this is just a word of warning. It's not the performance gain that some people might unknowingly guess that it is. And that the solution to get around this is to really think about the ready-made universal functions that are available in NumPy and try to find a NumPy kind of way of doing it. It'll be faster almost always. And alternatively, if you really can't make NumPy do what you want, but you're still trying to use NumPy itself, you can use their C API to build your own universal function type for whatever it is you're trying to do. I promise you that's more work, and I'm going to show you another way later to make your own C extensions to get away from dynamic typing that are, I think, easier. But first I want to talk about LRU caching, or least recently used function caching. The least recently used part is a heuristic about what to decide to keep in cache versus dump or move to different levels of cache. So in this example, caching is actually provided very easily. Function caching is provided very easily with the function tools standard library, where you import LRU cache, and you can use it as a higher order function or a decorator on your function. And it takes in a single important argument of how many times you want to cache this function. But what do I mean by that? For a given function, you'll have arguments, of course, and return values, and they're sort of paired together. So what this says is you can hold in cache, or so to speak, memorize or memoize 32 results of computing the input argument to output, so that in the future, if you recompute with those arguments, instead of actually recalculating the result, it will look up the answer to the result instead. And that tends to be faster from cache, depending on what the function is. If it's really cheap to compute, then maybe it won't save you time, but very often it saves you time. This is just an example. The best use case for this is when you're using functions over and over again and they're recursive. Not that that is a requirement, but for example, computing Fibonacci numbers, if you use this function multiple times, you get to use the partially computed results of previous iterations to compute the next iterations kind of for free by lookup instead of by calculation. All right, language extensions. So the gist of this is, well, it's a little bit unavoidable that Python is it's dynamically typed, and that even the performance that you get from NumPy is mostly, not entirely, but mostly due to the fact that in the back end, it's just C with static typing loops. So how do we get our own C extensions for things that are not so readily finagled into being a NumPy statement? And there's different libraries available. Certainly there's the C-types library available in Python that allows you to build your own bindings to existing C libraries. There's also CFFI that is supposed to be syntactically nicer, but achieve a similar goal. In my opinion, for writing, not binding to existing code, but writing my own extensions, that Python so far has been my favorite. It is the closest to just writing Python with some small modifications, as you can probably find. And what you can see in this example is that you have to write a pyx file instead of just a .py file. And the declarations of types and such are different. So at the beginning of this function test, we use cpdef. And cpdef is a way of defining the function that will be available in both the underlying C code and in your Python code later, that it can exist in the Python namespace. cdef alone is for the C part of it only, the C compiler. And what you can also see is that there is declarations of integer types for this particular function, but Python provides doubles and other things, characters and such. So you can notice, especially narrow in on the for loop here, that it says for I in range of X, but right above that, I actually ended up having to define cdef int I. And in vanilla Python will automatically go, well, if you give me a for loop, I'm just going to assume that I is a dummy variable, and I'll create it, and I will use it in whatever way ends up needing to make sense, including if you change the type of I as you're actually computing these loops. That's part of the flexibility of dynamic typing. But when you're doing repeated numerical operations, kind of in a sort of Bayesian statistics metaphor of like, you can have better priors than just assuming it could change anything to anything at any time. Instead, it's useful to go, no, this is going to be a number, an integer specifically. So in addition to writing your .pyx file, you will have to make some small modifications to your setup.py file, and that will handle the compiling, including all of the stuff that you have to do with linking libraries, if you know about that. And that for examples that I've seen, including this one, that you can sometimes get like 150 to 200 times speed improvement for using a C extension with Python over just having done the naive implementation with Python. So pretty big gains. I've heard that well, I know for a fact that there's at least one professor here at UNBC that uses Fortran, and I know there's also a couple of students that do as well. So I wanted to give sort of a Fortran related example. This is not a Fortran extension, it's still a C language extension. What happens with this particular tool, F2Py, which is actually inside of Numpy, and the sort of the history behind that is they took some lower level libraries like LPAC from Fortran, linear algebra library, and some other things, and they wanted to build a way of sort of wrapping Python around that. And what they ended up finding was easiest was to actually write a language translator. Instead of trying to get Python, which is C-based, to talk directly to Fortran, they wrote a translator that takes Fortran code, turns it into C code, compiles it with the appropriate bindings so that it's an available C extension for Python. So it's on the command line. And again, sorry for like the Linux tux peeking over the shoulder there, but this can run on any system of you run Python and you use -m to specify that you want to use F2Py, and -c for specifying some compilable code. fib1.f is just a hypothetical Fortran implementation of computing Fibonacci numbers, and -m to say what you want the final extension to be called. And the easy convenience of this is it's like one command line. And then if you go then into Python, you can just import it. Of import fib1, you have to build an array to sort of pre-specify the size of it. But then you can call your Fibonacci subroutine just by going fib1.fib on your array, and it will occupy the Fibonacci sequence for 8 elements of it into that array. So it's, it's not something that I have done a lot myself, but I want to make people generally aware that this exists if you're more on the Fortran side of things and want to connect that with some easier scripting. So if you want to know more about this, you can look at the user guide and reference manual that's available in the Numpy documentation. All right, parallel processing. I have done this a lot, mostly simple cases of it, but I can tell you that this is a great way of getting some performance, especially out of scientific computing problems where there can be there tends to be a lot of opportunities for parallelism. Where you basically have a collection of CPUs or cores, and you have some problem, and you want to break that problem into distinct parts and get the CPUs to separately solve those distinct parts of the problem on their own. And this involves, at the low level details of it, creating a process manager and figuring out how you're going to talk to each of the cores to put information back and forth and aggregate it back at the end. And that's done very simply and succinctly of just from the multiprocessing library, which is another standard library of Python. You can import this pool object, and assuming you've got some function f defined, and again, I'm sort of thinking numerically here that you return the square of that number, that you can use a context manager, which is not the same as the process manager, although the pool part happens to be a process manager. The syntax of like with foo as bar is a more general Python feature. And that helps control namespace stuff, but you don't have to use it here. It's good practice. So anyways, with pool, you pass in this case 5, but however many cores you have, and give it a name for the namespace of P. And then you can go p.map. And what map will do is it'll take in as an argument, first of all, your function that you want to basically run that function a bunch of times with different inputs. And then you also pass in an iterable of various inputs that you might want to try. So those will be split apart and computed into, and F will be computed on them separately in parallel. So this is very syntactically simple, and yet, in some cases it can save you a multiplicative factor proportional roughly to the number of processors you have. So for convenience, there's sort of a workaround. If you have a function f that has that should be taking in multiple arguments, you could secretly pass in an iterable as one argument and then unpack that iterable inside of the function. But it's more direct and simple to use p.starmap, which supports multiple arguments. You pass in an iterable of tuples, and it will appropriately unpack those arguments into your function. The only thing I'd say is a limitation that I've particularly found for easily parallelized problems that you can still run into it being slower than if you hadn't used parallel processing is when the input problem is really small. That it turns out that the overhead time of just managing how the processes are going to split the data up and send it to those and get it back and re-aggregate them, that for really small data sets, that's actually not a good use of time. The communication overhead itself actually takes longer. Another type of concurrency, which I guess I didn't define concurrency, but roughly we'll quickly define it as that, you know, you have some kind of shared resources over time, and that over time you kind of share that resource between different things. In true parallelism, you have things happening exactly at the same time, but separate in sort of space. Asynchronous is where you're sort of weaving different processes using the same processor. So asynchronous can still be single threaded, where you're weaving different processes back and forth. And I'll try to give a motivating hypothetical example, or motivating story anyway, in a moment. But just to explain how quick it is to get started with asynchronous programming in Python is that there's a built-in standard library called async.io. And you have to change the syntax a little bit again. You have to have this async in front of your definition of your function statement. But the point is you can then write some part of your subroutine first, print hello in this case, and then use the syntax await with syncio.sleep, just representing wait a while. In practice, that can be replaced with doing something else, like calling some other computer over a network. And then once you get that message back from await, then you print. But the cool thing is that you don't have to waste time with your computational resources just sitting there in idle, waiting for the answer. And I'll try to give a metaphor in a moment of why that's the case. But because this is sort of a non-standard syntax and they had to figure out a way of parsing it into the runtime environment, you also have to do this asyncio.run, pass in your subroutine there. All right, so if you don't already know about asynchronous programming, I'll try to give it a motivation with like a little hypothetical story of that. You know, imagine that you call the bank and you need to talk to them about your finances, and the bank answers you but says, okay, well, we can talk to you in like 15 minutes. We'll put you on hold, right? Well, what are you going to do? What would be the best use of your phone time? You could just sit there for 15 minutes doing nothing on your phone, so to speak. And this analogy breaks down a little bit. Pretend that the main thing you want to do with your phone is make phone calls. Because you could obviously, I don't know, watch YouTube or whatever, but assuming that you want to make as many phone calls as you can with that resource, is in an asynchronous setting, you can call your friend while you're waiting for the bank to get back to you. And when you're done chatting with your friend and the bank gets back, you can then flip over and talk to the banker. So that's the rough analogy. Is it's saving you resources in the sense of not wastefully just waiting for answers from other computers or other pieces of hardware. And that's where that idea of it's best for IO bound, input output bound problems, where you have got some level of communication going on between devices and you don't want to waste time just waiting, as opposed to CPU bound problems where your resources are at max and that it's not a communication overhead problem or anything. It's just, you know, some things are slow for other reasons. Okay, the last thing I want to talk about is there's a package that I'd say the best use case for this package, and I think it's very applicable to many engineers and scientists, and so this is why I want to give it some special attention for a moment, is that it's built to take somebody who has written some code in, say, Numpy and go, okay, great, you've written the best Numpy code that you can write as far as Numpy goes, and you still want to have some important performance improvements on top of that. So the first thing is it's very Numpy friendly and you get to keep your statically typed mathematics, and that's very nice. But it also allows two different types of compiling. One is just-in-time compiling, which as it sounds, or maybe sounds, I don't know how intuitive it is, but the gist is at runtime, it will decide to compile the pieces of code that can be compiled or are allocated to be compiled. and that those compiled parts of code will run faster. If you get into learning how the module works, it goes back to basically decorators and specifying arguments in decorators, kind of like with the LRU cache example I gave, where you pass in an argument. And then also ahead of time compiling, which is the more standard notion of compiling, that you first, compile the source code and then you can call it later and it'll be static typed and fast and such. Some other things that it does include parallel processing, that you can, just as I said with the multiprocessing example, very easily take a numerical task and just split it off amongst processors. And GPU computing, which is something I'm aspiring to get into a little bit more in my own work, where you use a different type of hardware, which a lot of us are familiar with as the graphical processing unit. And that's especially good for linear algebra type of math operations, partly because GPUs are designed originally to do graphics, things like computing changes of perspective, and that ends up being changes of basis and linear algebra type stuff, right? Multiplication of matrices and vectors and such. So it turns out that we can use GPUs for a lot more. Very popular for GPU use now is things like training artificial neural networks, but I'm sure it applies to a wide variety of different numerical computing type of tasks. And from what I've been reading of their documentation, that they can use NVIDIA GPUs and AMD. Many people have NVIDIA, and it's fine if you have CUDA. CUDA, if you know about that, it's just a different framework for handling GPU computing, but it is unfortunately NVIDIA hardware specific. So it is usually good news to people like me that unfortunately have only AMD hardware, that you can also take advantage of GPU computing. So the last point on this is that it's meant to interoperate very nicely with, as I said, Numpy, but also if you write your own C extensions additionally, that it doesn't have any fundamental compatibility issues if you make C extensions with C types or CFFI or Python. And with that, thank you so much. And if you have any questions or comments, I'm certainly happy to engage with those. And if you want to stick around later to have discussions, that's also perfectly all right as well. And I'll pass it back to Jeff to moderate.
Thank you very much, Galen. That was fantastic. I want to start by saying I do think the correct answer was to go on YouTube while you waited for the bank, but second would be call your friend. That's just fine. There was a question here in the chat from Hamid. Can you read it, or I can read it out loud, or do you see the chat question?
I do not.
Okay, what is the best way to profile a Python code that runs on the GPU/CUDA? Can you pass TensorFlow tensor on the multi-processing function that you presented?
I don't know. That is definitely an empirical question. You're just going to have to try it out. I would suspect that it would do profiling. The more difficult question with a very large package like TensorFlow is the usefulness of, sometimes it will, like packages like TensorFlow are sort of sitting on top of a whole bunch of different submodules. And so you may get an absolutely ginormous profiling result, but it could be useful. Yeah, I don't know.
Thank you. Are there any follow-up questions? Andy, your mic is off. Are you asking a question?
I was gonna wait if people ask questions, but
you can go. Go ahead. You're ready.
Yeah, actually, I like you presented an example about vectorization, because I actually, can I share a screen? As I have an exact slide on this when I teach the numerical course. So, and I'll point Galen is actually pretty comparable times that we're looking at things like this. So, sorry, I have to find lecture notes. Just have to find the.
Okay. That's decomposition. That's cool. Well, there's a good example for GPU computing.
Well, yeah. So, or just yeah. So talking about the sum, like a lot of operations in science computing is like dot product and sum and things like this. So obviously, I'm calling the NumPy sum instead, which supposedly does vectorizing on its own, and it does get really good performance compared to if you loop over, the Python, right? It's like 1,000 times. This is partly pretty extreme, but usually you don't get that much performance. But the dot product is actually another one that is used a lot, right? That matrices, any kind of matrix decomposition, we use dot products. So if you try to write your own dot product compared to the vectorized NumPy version, it's like 400 times, right? So those are really important things that actually is really relevant. If you're doing simulations, you're going to sit there on the computer 400 times versus you're done in an afternoon, right? So it's huge. It's something I do emphasize in the numerical course. So it's good that you bring it up
Yeah, it's a really good point. And what's super slow there is the dynamic typing. If you're looping, every time you loop, it has to completely recheck what all of the types are, which sounds silly when you know that every time it's going to be the same numerical type, right? And that's the advantage of static typing. It's so much faster to static type loops if you know that you can rely on those types being compatible.
Is that the same reason why, like in MATLAB, the doing vectorized calculations is better than loops? Is it the same reason always?
So let me actually, to that point of like vectorization versus static typing, is that vectorization is additionally this idea of sending collections of instructions to the CPU in little batches. Tends to be a little bit faster. So to just sort of demarcate that, because they kind of go hand in hand in Python and NumPy, and you don't see that in the back end. I suspect it's true in other things, like I've used Octave, which is the sort of cheap MATLAB.
Right. Yeah. Okay.
But I'm sure that it's a similar idea of, if there's vectorization, if they're using the term in the standard way, that means they're sending little groups of operations, and that does tend to speed things up. And also that, in the back end, if it's doing static typing versus dynamic typing, that'll also be a speed improvement for sure.
Are there any follow-up questions for Galen? Okay. Oh, Todd has a question here, I think.
And just because I gave up programming years ago, like when Fortran, we're still using Fortran, but I programmed in all sorts of languages. So just out of curiosity, machine code, if you program at the level of machine code or assembly, you're going to get significant increments in speed, right? Because I mean, ultimately, any higher language has to be compiled down into something.
Yes, if you're really smart, which I am not in that sense. This point I was talking about with the best code is the code that's already written applies to compilers as well. So some people will say something along the lines of like, well, why would you ever write a higher level abstraction language? Why would you ever bother with that if you could write faster, lower abstraction languages? And the answer is partly that saves you time as a human in your own productivity. In principle, if you wanted to write, if you looked up for your particular physical architecture hardware, you could look up what that instruction set is. And in theory, you could write a program that is way faster than any system is, any automated compiling system will do. But in practice, compilers are so much smarter than humans because they have decades of human expertise put into like tweaking all the little things of why certain instructions on specific pieces of hardware are better that are a mystery to me usually.
What is the time factor difference? I mean, you're talking there in some of those instructional systems were in the orders of microseconds or tens of microseconds, which gets you down in the range where you are talking about hertz, nanohertz, or nanoseconds, which is a gigahertz, right? So how much would you save if you were to go an assembly route?
I don't know, actually. I can tell you more about my experience of taking my slower Python code to C extensions, that sometimes goes from something that'll literally take hours to something that literally takes minutes. But as far as like the difference between if you compiled some C code and it's reasonably good C code versus if you had written in assembly, I'm not sure. It's a good question. But I would imagine that the best use case for that type of customization is on like small pieces of embedded hardware where the point there is you have very limited resources in terms of time to waste and space to waste, where maybe these very, very tiny increments matter, but what exactly quantifiably they are, I'm not quite sure, Todd.
So what would be the other, because the other extent, I mean, Fortran is a very old language and it's been around longer than I have. So is Python that much faster than Fortran? Like, I mean, if you were to write the same program in Fortran and in Python, would they run the same speed, or would you be able to see incremental increases in speed of a significant value?
You know, if you write sort of what syntactically looks equivalent in Python versus Fortran, your Fortran code is going to be way, way super fast for sort of a couple of reasons. One is the usual like compiled static type conversation that Fortran is statically typed. You declare the types ahead of time, you compile it, the program is going to assume that those are the types that happen to be there at runtime, and that gives you speed improvement. But the other subtle thing about Fortran that actually makes it sometimes even faster than C a little bit is the fact that it indexes columns first rather than rows first. And that subtly your Fortran code can be a little faster than your C code because of the way that certain linear algebra operations happen. But in the broad strokes, like compared to just Python, Fortran is going to run circles around it. Orders of magnitude run circles around it.
Okay, thank you.
You're welcome.
May I add that we have used machine code in Computer Science 231, and it was really painful to code in. It was not user-friendly at all, and we were not exactly sure of what we're doing. So I think programming languages are a blessing.
Unfortunately, in my brain, I could program an assembly much easier than I could program in other languages, but that's just because my brain's mixed up.
Debbie, do you have a question?
No, I was just going to add that it's nice that somebody said something about Fortran, because that is the program I use. Not that I ever do any programming, but I thought it was like out of date and dead now because of all of the newer languages. So, and I'm happy that my knowledge is not completely unuseful.
Fortran,
Not that, I mean, other people still do the work.
I'm not sure how big is the library files for Fortran compared to Java and Python.
Oh, I don't know. Yeah, you'd have to go check the file sizes, but yeah, the apples to apples comparison of how much byte space a C program versus a Fortran program is, or a Java program. I don't know. It's a good question. Yeah. The hard drive space is usually not the most limiting part, but usually when it's loaded into memory, that's where it's a pinch, right?
All right. Well, if you have no other questions, I want to thank Galen one more time. That was fantastic. That's something that we all could have done ourselves, but it was nice to have you do it for us and teach us all some stuff. That was really, really great. You obviously have a fantastic amount of knowledge in that stuff, so we really appreciate taking the time to show us. So thanks again.
It's a pleasure. Thank you.
I will stop the recording, and then if anyone has any follow-up questions, they can stay and chat with Galen for a few minutes. Stop.